Now let us see and examine various techniques that are used to handle the control hazards. What is the control hazard? If there is a branch instruction, we don't know what will be the next instruction unless the condition in the branch will get evaluated. Let us see once again. There is a branch instruction, that is, let us say in the 24th address, there is a branch instruction which is called BG 450, okay, which requires to evaluate a condition. If the accumulator is equal to 0, then the control will go to a subroutine's address 450. If the condition is not satisfied, the next instruction will be fetched. Okay, 25. The program counter value, you know that, 25. If the condition gets executed, we will take this instruction. The address part of the instruction is going to specify the address to where the branch is taken. Okay, and anyhow, program counter is going to specify the next instruction in case if the condition is not satisfied. Okay, but we don't know what is the next instruction. Next instruction could be 450 upon condition is satisfied, or 25 upon condition is not satisfied. For that, we need to wait till the condition gets satisfied, till the condition gets evaluated rather. Where this condition gets evaluated? In the final segment, in our case in S4, in which ALU operation will be computed, the condition will get evaluated. So we need to wait till the current instruction, 24th instruction, crosses this S4 stage. Till then, there is no way I can enter this 25th instruction into the pipeline. Okay, so here also there will be a stall cycle which is equal to k minus 1. But fine, 1 k minus 1 is fine, but there will be several k minus 1s because every program has several branches. During every branch, there will be a k minus 1 stall cycles. There are 1,000 programs that are needed to be executed. Every program has thousands of the branches, right? In which case, each and every branch, if it is going to incur k minus 1 stall cycles, computer speed up will get drastically reduced, rapidly will decline. Again, we need to avoid this. So we are going to use various techniques to handle control hazards. The first technique to handle the control hazard is prefetching the target instruction. What is prefetching the target instruction? The moment the branch instruction is fetched, we don't know what is the next instruction. Next instruction could be either 450th instruction or 25th instruction, right? So what we do is simple. Get both instructions, 25th instruction as well as 450th instruction. Okay. Meanwhile, as the condition is being examined, what you do is you just fetch both instruction. That is, if the branch is not satisfied, if the condition is not satisfied, what is the instruction? If the condition gets satisfied, what is the instruction? Get both instruction. Okay. Definitely, once after the condition gets evaluated, you will be able to know which instruction to hold, which instruction to leave. So corresponding instruction you hold, and the remaining instruction you can leave, you can discard. Okay, in this time, at this moment, some time will be saved here, because if you wait till the branch instruction to get executed, then fetch the corresponding instruction, it will take a lot of time. Meanwhile, if you call both instruction into the CPU, that is taken branch instruction and non-taken branch instruction, there will be a lot of clock cycles saved. This is what prefetch target instruction. Fetch the instruction in both streams. One is not taken, one is taken. Not taken instruction will be your program counter's value. Okay. Non-taken instruction address will be your program counter value. Taken instruction address is available in the address part of the program. Okay, so get both instructions. Finally, Both are saved until the branch is executed. Then select the right instruction. Once after the condition is evaluated, based on the condition, either it is satisfied or not, hold one instruction and leave the next instruction. Let us say condition is satisfied. You need to hold 450 and you need to leave 25th instruction. Okay. This is how time will get saved when we prefetch the target instruction. Another technique to handle the control hazard is branch target buffer. This is one of the wonderful techniques and most widely used technique. Okay. Let us see what it is. You know, the instruction will get fetched initially. Okay. Instruction will get fetched initially. Let us understand that this is the fetch stage. Okay. Fetch stage. When you call an instruction, rather, when you fetch an instruction, the instruction will be available in the instruction register. There are two chances. The fetched instruction could be either a branch instruction or a non-branch instruction. Every other instruction is called a non-branch instruction apart from a branch instruction. Okay. Now, to the fetch stage, what I'll do is I will attach one buffer. To the fetch stage, I will attach one buffer. This buffer has the entries of the previously executed branch instruction and their target addresses. For an example, there is 45th instruction. This 45th instruction is a taken branch which is branching to 250. Okay. There will be 86th instruction which is also a branch instruction in the current program, which is a non-taken branch for which the target address will be 87 itself. If the branch is not taken, definitely the program counter value will give you the next instruction's address. Then followed by 120. Again, this 120th instruction is a branch instruction within the program and it's a taken branch which is going to 85. Rather, 185. And 140 is a branch instruction which is not a taken branch. So the target address is 141. Followed by 280, which is a taken branch. For this branch target address will be equal to 50. Okay. Now, there is a BTB associated for fetch stage of the pipeline. The moment one instruction has been fetched, we are going to have a lookup in the BTB. Okay. Is this instruction a branch instruction? If this is a branch instruction, you don't need to evaluate the branch. You don't need to evaluate the condition. Rather, if it is a branch instruction, there will be already an entry in the BTB. Okay. So directly you take it. For an example, 45th instruction has been fetched. 45th instruction has been fetched. For the 45th instruction, we are going to check an entry in the BTB. Okay. So now 45th instruction is a branch instruction. The BTB is going to handle, the BTB is going to have all the branch instructions and their target addresses. So here 45th instruction has been fetched and there is a corresponding entry in the BTB. That means that the 45th instruction is a branch instruction. Then what is the target for 45th? 250 is the branch target address. So without evaluating the condition itself, we can directly fetch the next instruction 250. Okay, if you don't use a BTB, what we need to do? First of all, 45th instruction needed to be fetched, decoded, and finally the condition is needed to be evaluated. Finally, then only we will be able to know whether the 45th instruction has a taken branch or a non-taken branch. But what we do is, every time when a branch instruction is executed, we are going to fill this BTB. Okay, definitely you can understand for the first time there won't be any entry in the BTB. For an example, the program is being executed for the first time. This BTB is empty. Okay. And 45th instruction is a decoded branch instruction. Then 45 will be entered in BTB. Once after the 45th instruction completely gets executed, then we also know what is the branch target address for 45. So the target address will be present here. Once after the program has been executed at least for once, for this program, there will be BTB entries. Again, from the next time onwards, when this program is executed again, there is no point in executing branch instruction. Okay, before evaluating the condition itself, if you can have a look at the BTB, it is going to give you the branch target address directly without evaluating the condition. So this is one of the beautiful technique in which way, in such a way that number of stall cycles will be drastically reduced. Okay, so when fetching an instruction, search a BTB. If found, fetch the instruction stream in the BTB itself. You don't need to evaluate a condition. If not, new stream is fetched and update BTB. That's it. This is what and how the BTB is going to get updated when a branch instruction is present. Every time when a branch instruction is fetched, immediately we're going to search within the BTB. And the BTB, if it has a corresponding entry, then that means that this is a branch instruction. Otherwise, it is not. If it is a branch instruction, it also shows you what is the target address. So directly go to the address and collect the instruction. Simple. This is what the BTB is all about. Okay. And then there comes a loop buffer. Okay. What is the loop buffer? If we can actually stay focused, let us, I will explain. 24, 25, 26, rather, 26 instructions are inside a loop. Okay. Loop is going to get repeated for 100 times, let us say. Okay. Now here, in the loop also, we do have a branch. After 26 instruction, we must branch to 24, right? For how many times? For 100 times, as long as the loop gets repeated. 26th instruction will branch to 24. Because this is necessary. Every time when loop gets executed, the final instruction of the loop will get branched to the first instruction of the loop. So here, we are going to use a loop buffer, which is just a small variation of a BTB, in which what we do is we use a register file by the instruction fetch segment. Again, this loop buffer is also associated to the instruction fetch segment. This register file stores the entire loop, which allows to execute a loop without accessing memory. So here in the loop buffer, what we'll store is all the values that are required for this loop. Okay, so that is, here we know that 26, 24, meaning 26 is the branch instruction and 24 is the target instruction. Okay, in which again I am going to maintain a register file R1, R2, R3, R4, in which the values which are required to execute this loop will be present. But actually the values are available in main memory, right? So when you use a loop buffer, what we'll do is, initially the first entry of the loop buffer will point the final address to the first address of the loop, because 26 will have to branch to 24, after which it will be followed by a register file. This register file is going to access all the values which are required to execute the loop from the memory. So you can clearly understand, as long as the loop gets repeated, we don't need to access memory. Whatever the values that are required by this loop are available within the loop buffer itself in the register file. This is what the loop buffer is all about. The rest of these two techniques are really simple. Okay, branch prediction. What is a branch prediction? Simple. Branch prediction is a schema. A schema which is going to predict the outcome of a branch. It is like an astrology. Like, we are going to consider a few factors of the program. Based on those factors, we are going to predict the outcome. That is, current instruction is a branch instruction. 24th instruction is BG 840. Whenever we come across a branch instruction, okay, we are going to run the schema. Schema is an analogy which is going to be made on the various factors of the program. Okay, this schema is going to predict the outcome of the branch. Okay, whatever it could be. It could be 25 or 840. It will be predicted by the schema. Whenever we have a branch instruction, we ask the schema. Okay, It's a taken branch or a not taken branch. The schema is going to evaluate all the condition and it is going to tell you within no time whether it is a taken branch or not. Okay, taking the inputs from the schema, we will execute 840 or 25. Okay, so it's a branch prediction, but understand prediction is always a prediction. It is as good as your astrology. Like, looking at the television to find out whether it is going to rain or not. There is no guarantee that schema works fine. Okay, finally, delayed branch. You know what is a delayed branch? I don't need to explain you guys because we already knew what is a delayed load. Delayed load is a compiler technique in which dependencies of the instructions will be found out and those will get separated. The separated slots will get occupied by the independent instruction. Similarly, delayed branch is also a compiler technique. Compiler technique in which branch instruction, I will write it here. Branch instruction and the next instruction will get separated by sufficient number of clock cycles, and these slots will be occupied by some independent instructions. This is what the delayed branch. Okay, now I will show you how delayed branch is going to look like. Okay, let us see this delayed branch. Okay, there are several instructions. Okay, now there is a branch instruction. Branch instruction, next instruction is obviously, whatever. It could be taken branch or a non-taken branch. So this branch instruction and next instruction must be separated by no operations, which is a stall cycle here. You can see that there are other instructions. Other instructions are entered into the pipe. Okay, but branch instruction and next instruction are separated. But with rearranging the instruction by using delayed branch, okay, branch to X and the instruction in X will be separated by those sufficient number of clock cycles. But in these stall cycles, I can use other instructions, that is add or subtract. So I can rearrange this instruction. So in this case, I don't waste even a single clock cycle. Okay, this is how delayed branch is going to work. These are the different techniques to handle the branch hazards, the control hazards, in which stall cycles will be reduced and the smoother operation of the program and the computer system is guaranteed. So the speed up will be sustained